Hi, this is Mrs. Villette, and this video is to connect the properties that we learned of logarithms last time to how we solve equations. So I'm going to solve some equations in a few different ways just to see how, even though your approach might vary, your final answer could be the same. Our first example is to solve the equation 2 to the x equals 5 in as many ways as possible, and then we'll check algebraically. So the first way that we could do this is just simply to use the definition of logarithms to translate. So 2 to the x equals 5 is equivalent to saying the log base 2 of 5 is x. So that would be the first way that we could solve this. Another way that we could solve this equation is we could take a logarithm of both sides, and I'm going to choose to take a log base 2 of both sides. So if I take a log base 2 of 2 to the x and a log base 2 of 5, we get the cancellation properties on the left-hand side that say this gives me just the input of x, and so we get x equals log base 2 of 5. The same answer that we got just by translating. Yet another way to do this problem would be to take a logarithm of a different base. You might wonder, why would I take a logarithm of a different base? Well, one of the reasons is that on your calculator you have some built-in logarithms, the common log, which is log base 10, or the natural log, which is log base e. So I'm going to choose to apply just a log or a common log on both sides. Now what this gets you is the exponent rule that says these don't quite cancel, but I can bring down the x as a coefficient. So now I have x log of 2 equals log of 5. We're trying to solve for x, so in order to do that I need to divide both sides by the coefficient, which is log of 2. And I get x equals log of 5 divided by log of 2. Now this is the only answer that doesn't quite look the same as the others. So one way that we could compare is we could actually evaluate all of these. So the answers that I have are log base 2 of 5 versus log of 5 divided by log of 2. Now, prior to the advent of newer graphing calculators, you wouldn't have actually had a way to evaluate this expression anywhere in your calculator. They didn't have built-in bases other than common log and natural log. So your only choice really would have been to evaluate this side. If we evaluate in Desmos or in one of the newer calculators, we would enter it in as log 5 comma 2 into some of the newer TI calculators, and we're going to get about 2.322. If I enter this other expression into my calculator, I also get 2.322. So I end up getting the same answer for these, which leads me to conclude that it's not a versus, one versus the other. It leads me to conclude that these two expressions are actually equal. And that leads us to something that's called the change of base formula. So what this change of base formula actually allows us to do is it allows us to change from a logarithm base b to a logarithm of base c. So this allows us to go log base b to a log base c. Now it doesn't quite change it all the way to a log base c. There's some division here that goes on. So notice log base b of x is log base c of x, but then it's divided by log base c of b. Usually we're going to want to change to a logarithm that we have easy access to. So log, for example, so log of x over log of b, or natural log, so ln of x over the natural log of b. Notice that whatever the argument is of the logarithm goes into the argument of the new logarithm, and whatever the base of the logarithm was goes in the argument of the denominator. So especially if you have one of the older TI calculators, this is a formula that you need to know how to use to evaluate logarithms of different bases. Okay, now I'm going to show you some of the other log properties in action by solving equations in different ways. And I just realized I forgot to check algebraically on that last one, so I'll go back to that maybe at the end of the video. Okay, so we have 2 times 5 to the x equals 100. The best thing to do, the most efficient thing, would be to divide both sides by 2 to get 5 to the x equals 50. And then we could just translate that to a logarithm. Log base 5 of 50 equals x. Now we also know that we have a change of base formula. If I wanted to evaluate this with regular logarithms, I would do log of 50 divided by the log of 5. Okay. Another way to do this problem is not the most efficient way. It's to go ahead and take a logarithm of both sides prior to isolating the exponential. So I'm going to take a log base 5 of both sides. And I like the idea of doing a log base 5 because it relates to the exponential. So log base 5 of 2 times 5 to the x equals log base 5 of 100. So let's add that base 5. On the left-hand side, I can split up using our log property for multiplication that says I split up the arguments and add them. And on the right-hand side, I'm just simply going to leave that because log base 5 of 100 is just a number. Now back to the left-hand side, I have a cancellation property going on right here that gives me just x. So I have log base 5 of 2 plus x equals log base 5 of 100. Now I'm trying to get x by itself, so I need to subtract this log base 5 of 2 from both sides. And I get x equals log base 5 of 100 subtract log base 5 of 2. Now this doesn't look like either of the answers I have. I do, however, have a log rule that says if I have 2 logarithms that are subtracted, I can divide their arguments. So I end up getting the log base 5 of 50, which, if you'll notice, is the same answer that I had when I did this the easier way. Okay, let's go ahead and check algebraically. So checking algebraically just means plugging the answer that I got back in to my original equation. So I have 2 times 5 to the x equals 100, and I am going to replace the x with the log base 5 of 50. Now this expression right here is a logarithm of base 5 as the argument of an exponential with base 5. Those two things are inverses, so they cancel each other out and give you just the input of 50. So this ends up getting me 2 times 50 equals 100, which checks. So my solution set is just the log base 5 of 50. And if they asked for an approximation, you would go ahead and put that in your calculator, however you normally put logs of different bases in. So our next equation involves 2 logarithms, and we have not been able to solve equations with 2 logarithms up until this point. Fortunately, we have a log property that allows us to combine two logarithms that are subtracted. So it says the log of m minus the log of n is the log of m divided by n. And this works for logarithms of any base so long as they're the same base. That means I can simplify this to log base 2 of x over x plus 1 equals negative 1. The easiest thing to do at this point is to translate 2 to the power negative 1 equals x over x plus 1. You could also do this trick, which is to raise both sides of the equation as the exponent of something with a base of 2, because that allows us to use a cancellation property right here and get that x over x plus 1 equals 2 to the negative 1. Notice that's the same equation I have here. I will change this 2 to the negative 1 to a 1/2. So 1/2 equals x over x plus 1. This is a rational equation, so multiply both sides by the lowest common denominator and then cancel. So 2 cancels on that side and x plus 1 cancels, and I'm ending up with x plus 1 equals 2x. Simply subtract an x from both sides and you get 1 equals x. So the instructions say to check numerically and graphically. So to check numerically or algebraically, we're just going to plug in the answer that I got into the original equation. So log base 2 of 1 subtract log base 2 of 1 plus 1 equals negative 1. Now log base 2 of 1 is 0, and now I have minus log base 2 of 2. Does that equal negative 1? Log base 2 of 2 is 1, so negative 1 equals negative 1. So our solution set is indeed 1, and I'll show you in a minute what the graph looks like. So here I have gone into Desmos and I've entered the left-hand side as a y equals. So I have y equals log base 2 of x, subtract log base 2 of x plus 1, and then I have y equals negative 1. And the point of intersection is here. Based on the scale, I can see that that is at 1, negative 1. Of course, we are looking just for the x-coordinate of the intersection. So the x-coordinate of the intersection is at 1, and so we're going to say that our solution is x equals 1. So let's try one more example with logarithms. Again, we have two logarithms, but we don't have any other numbers. So I have a log on one side and a log on the other side. The best thing to do in a case like this is to use the cancellation properties. So what we're going to do is make my equation the exponent